is the 19th day of this lecture series, and I would request SC ma'am to kindly introduce our speaker today.
Okay, thank you, Navonita, and also Navonita and the other organizers for organizing the March Alumni Lecture right within March 2021. Today is the 31st of March, and despite exams and everything, they could organize it. So great. Now, I think it's my greatest pleasure to introduce the speaker today, Sagnick Mukherjee, who just graduated from our master's program in 2020 and went to UC Santa Cruz as a graduate student. He was an undergraduate student from 2015 to 2018. Now we generally invite we generally invite speakers who are not really our recent alumni, because once you get to do your PhD, you need some time to go do, you need some time to do some substantial work so that you can get back to your alma mater and present it. But that's the real introduction of Sagnick, because he is that kind of student who doesn't need any time to, bring out the joy, do exceptional research in no amount of time. And so Sagnick I'll just share one anecdote. So Sagnick came to me as a first year student and said that I want to do research with you, I'm interested. And then rest is history, because he's the only student I have worked with so far who has given me so much of inferiority complex, because he would do work so fast and I just could not match up with the speed. And you can see just in few months after joining the graduate program, we had to invite him for this great work that he did on exoplanet atmosphere. Now just some laurels, and then I'll get to Shag, and I'll just give the microphone to the speaker. So Sagnick was our topper in the BSc batch. He was the topper for our MSc program, so two-time gold medalist. He got offers from 6 top universities in the world, and he's now working at UC Santa Cruz on exoplanets. And UC Santa Cruz is regarded as one of the top 3 places for exoplanet research in the world. Sagnick was the recipient of the very, very prestigious Indo-US SNBOS Fellowship. And I expect that we have many youngsters in this audience who would take the legacy of Sagnick and make me and many of us as much proud as we are even more proud than the pride we feel and enjoy about our speaker today. So without further say, without further boredom, let me ask Sagnick to excite us or share his excitement on exoplanets, exoplanetary atmosphere. Sagnick, please.
Thank you, ma'am. Thank you for this introduction. I really enjoyed my time at Presidency, and I always think back what all of us have done in those years. And yeah, let me just share my screen. Can you see my screen now?
Yes.
Yes.
Okay. Okay. Great. Can you see my cursor?
Yes, we can.
Okay, great. Thank you for that introduction. And so I will be talking about exoplanetary atmospheres with reflected and thermal light. Now, I would in a second, I will come to what these are. But let me first introduce you to exoplanets. What are exoplanets? So we know that our solar system has 8 planets, which are rotating around our sun. But then there are so many other stars in the local universe. We know about so many other stars, and there's no reason why those stars shouldn't have planets rotating around them. And that's what we call exoplanets. So exoplanets are planets which are not in our solar system, which are in rotating around other stars, or they can be just freely floating around as well. So exoplanets are planets outside our own solar system. Now, this is just an animation of how an exoplanet system might look like, very similar to a solar system, or it can be very different as well. So, in the past 20 years, basically, more than about 25 years now, before that, we didn't know of any exoplanet. We only knew about 8 planets rotating around our sun. But right around from 1990, we discovered the first exoplanet. And then the field just had a boom. Within this 25 years, we now know of 4,360 something exoplanets as of today. So apart from our 8 solar system planets, we know of so many other planets in the local universe. And what this video shows you is basically keeping the solar system at the center. It shows all the other exoplanets near the solar system. It shows their sizes. It also shows their temperatures from their color. So you can see that this is a whole, whole new set of planets. Starting from only 8, we now have so many diverse planets we already know of. And this is just, the field is just beginning with telescopes like James Webb Telescope and other telescopes in the line. This will only go on increasing. Now, so the first question is, why should we study exoplanets? And there are 2 broad reasons. The first one is because when we look just at our solar system, we only have 8 planets, but that does not tell us the whole story. Because before exoplanets were discovered, we had some ideas about how planets used to form, how planets are, how their atmospheres are. But after exoplanets were discovered, we were totally surprised by many unusual things which we did not expect just by looking at the solar system. So there is one population reason that why we should study exoplanets. But then there's another reason, which is to find another Earth. The goal of finding another planet just like ours, which is habitable maybe. So those are the 2 broad goals. Now, just to give you an idea of the boom in the exoplanet field, this is a plot of the number of known exoplanets with time. You can see we started in 1990 from 1, and then we went on to about 4,000 now. And if you do some kind of statistics, you would note that the doubling time of known planets is about 28 months. With the COVID, we always are hearing about doubling times of COVID spread, but the doubling time for exoplanets is about 28 months. Within every 28 months, the number of known exoplanets approximately doubles. So yeah, this is just a boom in astronomy. But with so many exoplanets, now after having this huge sample of exoplanets, we are starting to ask the question that what are the atmospheres like in these exoplanets? Like Earth has its own atmosphere. Now we are asking the question, like, what are the atmospheres in these exoplanets? But before going into that, I would like to just give a brief intro into how we how we detect these exoplanets. And I just wanted to pause a minute and say that if any of you have any questions, please stop me and ask them. I am happy to answer them within the talk. So please just stop me and ask them. So yeah, so how do we detect exoplanets? There are many ways, but I will touch upon the 3 broad, generally mostly used ways. And the first one is the transit method. So in the transit method, as is shown in the video, what you try to detect is the brightness of the star with time. Now, if you have a planet rotating around the star, and if it is crossing your line of sight, then at some point, the planet will block some light from the star. And with a Jupiter-like planet, this light will be very close to the star. This will be about 1% blocking of the light. So if you look at this light curve, it would show you a dip because the planet is blocking some starlight. And that's basically the transit method. You would try to look for that dip in the light curve of exoplanets, of the stars. And what the transit method can tell you is firstly, the size of the planet, if the size of the star is known, and then also the separation of the planet from the star and other properties as like inclination and things like that. So this is a very useful method for detecting planets. And if you plot all the mass versus the time period, the rotational time period of a planet for all the known exoplanets, you would see this kind of a diagram. And all these green open squares are the planets which have been detected using the transit method. Now see that all these planets have small periods. And from Kepler's third law, we know that period is proportional to the distance. And hence these are close by planets to the star. And transit method has kind of a bias to closer planets to the stars. And that's why you see that most of these planets are detected by transit method. Now, also it has a bias to giant planets. It can detect bigger planets more easily. Now, the next method is the radial velocity method. Now, if the planet is rotating around the star also should have a bit of rotation of itself, because the star planet system is rotating around their common center of mass. And what in this method, what you try to do is you try to detect the motion of the star, not the brightness, but the motion of the star. And what this GIF shows you is the Doppler shift of the starlight. When it's moving away from you, you see a red shift. When it's moving towards you, and you see a blue shift. And by detecting that circular bit of small circular motion of the star due to the planet, due to the gravitational tug of the planet, you can you can infer the presence of an exoplanet there. And the typical velocity that typically people detect 100 meter per second kind of velocity of the star. But if you want to detect an Earth around the sun, so if you want to detect another Earth in the universe, in some other system, the typical precision you would need is about 10 centimeter per second. So right now, the best precision with this method is about 1 meter per second. So we are still not there to detect Earths with radial velocity methods. And if you look at the same diagram of radial velocity detected planets, you have the red circles. And of course, radial velocity either detects small, less massive planets which are nearby the star, or it can also detect planets which are much farther away from the star, but they need to be very massive. And that's why you have these red points here. And so both these methods are great. And as you can, of course, see from this plot, that most of the exoplanets we know of are detected by these two methods most commonly. But the thing about these two methods is these are indirect methods. You are not really detecting the planet. You are detecting either the blocking of the light by the planet or the gravitational effect of the planet. So there's a third, more direct method, which is nothing but taking an image. So if you have a very good camera and you just take an image, you are lucky, then you might just see the planet itself. And what this GIF shows you is actually a GIF of 4 exoplanets rotating around a star. The star has been blocked with a black circle. And yeah, you are literally seeing planets directly, not by some indirect means. So this is called direct imaging. But here, the direct imaging has been done not using visible wavelengths, but infrared wavelengths, because planets have temperatures in this case of about 1000 Kelvin or cooler than that. And at that temperature, if you calculate the Wien's peak of a black body, you would have a peak at infrared. So planets are mostly emitting light in infrared wavelengths and not in visible wavelengths. Stars emit light in visible wavelengths. So this is called the direct imaging method. And of course, this is very hard to do because if the planet is not bright enough for your sensitivity of your telescope, then you can't really see it. You can't detect it. It will be lost in the noise. And also you need to suppress the halo of the very bright star. The star is much, much brighter than the planet. So that both of these makes this very challenging. So this also has a bias. In this case, we can only detect very young planets because young planets are very hot. And direct imaging is biased towards hotter planets because they are more brighter um, for their light. And what light you are seeing in this case is the thermal light of the planet itself. Because as I said, that planet has a temperature, and any body with a temperature emits thermal black body radiation. So this is the planet's own thermal light here. So these are the broad methods. And of course, these, you can see that very less number of planets can be detected via direct imaging. All the stars have been detected, and see that these have really long periods. And the reason behind that is you cannot detect planets with direct imaging very close to the star because the telescope's diffraction effects would make the planet lost in the halo of the star. So you can only go far away from the star and detect these planets. So these are the general methods which are used. There are other methods. I won't go into that, but you can of course read about that later. Now, but as I said, this is about detecting planets. But how do we detect and study the planet's atmosphere? Like we have an Earth's atmosphere. How do we detect these exoplanets' atmospheres? And how do we study them? How do we know about them? So again, there are three ways generally to know about exoplanet atmospheres. And the first one is again through transit spectroscopy. So whenever we talk about atmospheres, we do some kind of spectroscopy. We split the light into wavelengths. What transit spectroscopy does is, see, you have a star here, okay, and you have a planet going in front of it. And that's basically the transit method. But now what you can do is you can look at this transit at three different wavelengths. Now, if the planet has an atmosphere, then the starlight is passing through that planet's atmosphere, right, and coming to you. Now, if the atmosphere has some kind of gas in it, say hydrogen, helium, sodium, each of these gases absorb light at different wavelengths. And what will happen is, depending on what gas is in that atmosphere, the planet's size will vary depending on what wavelength you're looking at. Say, in this case, you can see the dip is higher in blue and green wavelengths, but the dip is smaller in red wavelengths. That means that the planet's atmosphere is absorbing more light in blue and green wavelengths and less light in red wavelengths. And if you just plot the planet's size in different wavelengths from the transit method, what you get is a transmission spectra, which has been shown in the right. And from this, you can tell that what are the type of molecules which are present in the atmosphere. And this is how most of the atmospheres of exoplanets known today have been characterized. We have found gaseous water, we have found gaseous methane in these atmospheres, and this is how we have done that, using the light of the star passing through the planet atmosphere and coming directly to you. This is a great method. This is the most used method right now. But there are other ways as well. As I said, that the planets have their own temperature. So they are emitting their own light as well, like a black body. And if you try to look for that light, that process is called thermal spectroscopy. What that means is detecting the planet's own light. Now, what will happen is the planet will emit photons, and those photons will pass through the atmosphere to come out of the planet and then come to you. And by doing that, they will carry all the signatures of the atmosphere itself, all the interactions the photon had to face with different gas molecules before coming to you, and they will carry those signatures. And by looking at those signatures, you can tell if the planet has, say, methane, oxygen, nitrogen, hydrogen, helium, and whatever. And this is the GIF I showed you earlier. And as I said, in this GIF, you see the planet's own thermal light. So yeah, so direct imaging right now is done in thermal light from the ground using telescopes like Keck. So this is thermal spectroscopy. But of course, you need the planet to be hot enough to detect thermal light. Otherwise, you cannot do that. And the third and the most exciting to me is reflection spectroscopy, which is earlier you detected the starlight passing through the atmosphere directly, basically grazing the atmosphere and coming to you. But what if you can detect the starlight which has been reflected from the planet and comes to you? If you really think about it, when you look at those beautiful images of Jupiter, Saturn, Uranus, Neptune, Mars, what you are seeing is reflected sunlight. Okay, so if you just look at night sky and you see Jupiter very bright, Jupiter is basically reflecting the sunlight to you. And that's, if you take a spectra of that light, what you will get is a reflection spectra of Jupiter, or the reflection spectra of, say, Moon. And of course, this starlight will interact with the planet's atmosphere and then come to you, and hence it will carry the information in about the atmosphere's contents, and you can infer about what there is in that atmosphere using that reflection spectroscopy. So with these three methods, I would like to move on to the part one of my research, which is probing exoplanetary atmospheres with reflected light. So the starlight which has bounced off the exoplanet, and come to you. Now, as I said, in this GIF, this is all direct imaging, but in infrared wavelengths. And this is the thermal light of the planet, not the reflected light, but the planet's own light due to its own temperature. But in order to detect this, as I said, you need the planet to be hot enough, like 1000 Kelvin, 1500 Kelvin, very hot planets, whereas Earth's temperature is only 300 Kelvin. Atmospheric temperature is kind of, in the ground, it's about 300 Kelvin. So these planets are no way similar to Earth or any of the other solar system planets we have for that matter. These are much hotter planets, and that's why these are called hot. If you have heard names like hot Jupiters, because these are really hot planets. But we can only directly image them because that's what we need to direct imaging in infrared wavelengths, them to be hot. But this can only be done from ground right now. But coming up is the Nancy Grace Roman Space Telescope, which was formerly known as WFIRST telescope, which is supposed to be launched in 2025. And what the Roman Space Telescope will do for the first time ever is do direct imaging from space. And that gives us a tremendous advantage, because when you are doing it from space, you do not have to deal with Earth's atmosphere itself. And doing it from space gives you much more contrast. That means that you can see fainter objects around the star. And that will actually help us to directly image planets, exoplanets, in optical wavelengths. And as I said, planets do not emit light of their own in optical wavelengths. So when you are directly imaging an exoplanet in optical wavelengths, what you are seeing is the reflected starlight. And that means that these Nancy Grace Roman Space Telescope and future telescopes like LUVOIR, if they get funded, but these are telescope concepts right now, LUVOIR and HABEX, what they will be able to do is to directly image planets, exoplanets, in optical wavelengths, and hence detect reflected light. Right now, we cannot detect reflected light from exoplanets because it's too faint for us now. But these telescopes will enable that. And what that means is, now for the first time, we will be able to see cooler planets, because cooler planets do not emit much thermal light. And hence we do not see cool exoplanets, like something like 200 Kelvin, 300 Kelvin, 500 Kelvin, which are much more similar to planets in the solar system, much more similar to temperatures of Earth. So these missions will help us to find a whole new population of planets, which we call cool planets. And hence, we will be able to do reflection spectroscopy of these cool planets. So this is very exciting. And so that's why we are thinking about reflection spectroscopy. And not only that, what information does reflection spectroscopy carry to us? Now, when we do transit spectroscopy of exoplanets, what happens is we can only gain information about the very top part of the planet's atmosphere, because the light has to travel a whole lot through the atmosphere to come to us, because it's grazing the atmosphere. So we cannot really infer what's deep in the atmosphere because it becomes opaque. And also, the transit spectroscopy cannot really tell us about things like clouds in exoplanet atmospheres, because what clouds do in case of transit spectroscopy is that they just absorb that light. And clouds generally absorb light in all wavelengths. So what that does is it just changes the normalization of the spectrum. And that can be very misleading. It can also tell us that there is atmosphere, more atmosphere, less atmosphere. So we cannot really do two things with transit spectroscopy. First, we cannot look deep in the atmosphere. And second, we cannot look at clouds. And clouds are really important in any kind of atmosphere, because clouds govern the thermal balance, the energy balance in the atmosphere. Clouds can trap a lot of heat in the atmosphere. That's why when it's cloudy before rain, you feel a bit sweaty. And clouds can also reflect a lot of starlight back in the atmosphere. So clouds can at the same time heat up the atmosphere by trapping heat, and it can also reflect back a lot of starlight back into the space and maintain a cooler atmosphere. So clouds are really important for any atmospheric system. And the good news is reflection spectroscopy can tell us a lot about clouds. Just to give you an example, this is the reflection spectrum, moderate reflection spectrum of a Jupiter-like planet. The left is if Jupiter didn't have clouds. And you can see the Jupiter is not very reflective if it didn't have clouds. So it wouldn't look that bright in the night sky as it does now. But if Jupiter had clouds, like in the right panel, you can see that the reflection spectroscopy is completely different, first of all. It looks completely different. Secondly, Jupiter becomes very reflective. For example, Venus also has a lot of clouds, and that's why it's very bright in the night sky, because it reflects a lot of sunlight because of those clouds. So clouds have a dramatic effect on reflected light spectrum. Now, why is this a good news? Because it tells us three things. First, which I just said, that reflection spectra can tell us a lot about clouds. Second, in order to predict the reflected light spectra of a planet, we first need to account and model the clouds really well. We need to understand and model the physics of clouds well to predict reflected spectra in the first place. And the third, and which is the most important point for me, is say after 5 years or 4 years or 6 years from now, you get the reflected spectrum observation of a planet. Now the question is, how do you interpret that observation? What complexity of clouds do you need to take into account to interpret that observation? One might say that model the clouds as complexly as possible, but that is not a great answer, because then you might be overfitting your data. And secondly, while you are trying to interpret this kind of observation, it takes a lot of computational time. So if you have a really complex model of cloud where everything is like a very physicsy and microphysics of everything, then it would take forever to interpret one reflected spectrum observation. So due to those 2 points, we need to figure out that how to deal with clouds while interpreting these future observations. So that becomes my main point. And we turn this into a question, our research question, which is what I just said, which is how complexly you need to deal with clouds while you are inferring the atmospheric properties from reflected spectrum observation. For example, say you get a reflected spectra of a planet, say a planet, and you want to know that what is the amount of methane in that atmosphere and what is the amount of water in that atmosphere. While doing that process, how do you need to model the clouds so that you get the best possible answer, which is possible from that data? And that is the question. How do we deal with that complexity? of clouds. And to answer this question, I have a systemic flowchart because flowcharts makes me feel good. And the first step is to choose planets which are future targets for reflection spectroscopy. Of course, you cannot get a reflected spectra of all the exoplanets. There are some planets which would be more favorable for reflected spectra observation. So the first step is to choose some planets like that. The second step is to model their reflected spectra. With very complex models we have right now, we can do that. We can predict what the reflected spectra would look for that planet. The next step is to simulate observational data from the model spectra. So what you are trying to do is you predict that theoretically the reflected spectra for this planet should look like this. And then you say that what if a real telescope observed this planet? How would the data look like? Because a telescope has many effects, like it adds noise to the data. Okay, it has a limited spectral resolution. And all these effects, of this instrumental effects, you take into account. And then what you do is produce a fake data for the planet, okay, from this modeled spectrum. Now, with that data, what you can try is you can blindfold yourself. You say that I did not produce this data. I have not modeled this planet. I don't know anything about this planet. I have just this data and I am blindfolded. And then with some model, some simple model, you will try to guess that what is the water, given this data, what should be the amount of water in that planet? Given this data, what should be the amount of oxygen in that planet for that matter? Or anything, given this data, what should be the cloud in that planet? So you play that game of blindfolding yourself and trying to guess the right answer. But the main trick is you already know the right answer because you put in some amount of water, methane, ammonia, oxygen to produce the reflected spectra in the first place. So then you open the blindfold and compare your guess, what you have guessed about the planet and what is the true answer for the planet. So you try to see how correct your guess is compared to the true answer. And what you can do is try to infer the properties with various ways. You can infer it first in a certain way and then change the model, infer it again. And by doing this and comparing the answers, you can find the best possible way to infer a reflected spectrum observation. And that's what I am going to do. So this is the whole game of this work. So moving on to the first step, which is to choose a planet which is a potential target for reflected spectrum. This is a plot of the y-axis shows you the effective temperature of the star and the x-axis shows you the planet's effective temperature. So forget about effective. This is the star temperature. This is a planet temperature. Okay. And all the points in blue you see are potential reflected spectrum observation targets. And notice that all of this have low planet temperatures. And as I said earlier, that with reflection spectra, we can detect cooler planets. And those temperatures are something like 100 to 500 Kelvin. So these are really analogs of solar system planets, which we know exist from the radial velocity data, but we have never seen or characterized their atmospheres yet. We are waiting for these telescopes to take the reflected spectrum observations. So we need to choose some target among these blue points here. Now, one exciting target, and most of these blue points is a class of exoplanets called cool giants. Of course, you understand the meaning of cool because these are 100 to 500 Kelvin planets. So these are cool planets, not hot Jupiters, but cool planets. And giants means planets which are really huge. By huge, I mean typically the size of Jupiter. So cool giants are basically cool giants are Jupiter-like exoplanets, not hot Jupiters, not Jupiter-like planets which are really close to the star, but Jupiter-like planets which are actually at a Jupiter-like distance from the sun. So what we are trying to do is probing these cool giant planets with these observations and these exoplanets with these observations, and this has never been done because we can't really do that without reflected light right now. As I said, that this is taking one step closer to detecting an Earth-like exoplanet, because there's a consensus in the astronomy community that the way we would be able to detect the first Earth analog and say that the atmosphere is exactly or something like Earth is only by using reflected light, because Earth's radial velocity signal is really feeble, and it will take a lot of time to reach that kind of accuracy. People are trying, and Earth will give a very feeble transit spectroscopy, and Earth's thermal light is also very, very faint. So the only way an Earth can be detected is by the reflected light. So this is taking one step closer to that goal. So we will be looking at cool giant planets. And I will show you this plot where again in the y-axis you have the planet's temperature, and in the x-axis you have the planet's gravity. So Earth has a gravity of 10 meter per second square, and that puts this into perspective. So these are a bit higher gravity objects. And what we do for our work is we choose these 3 planets, okay? And the reason behind we choose these 3 planets is because they differ in their temperature. They start from about 120 Kelvin and reach up to 500 Kelvin. So we want to see if our answers which we get are same across the effective temperatures of the planets, which will come up in the future. So basically what you want to know is these are the 3 targets which we'll be using, and all of these are called cool giant exoplanets. So our first step is done. We have chosen our targets. So next, let's move on to the next step, which is modeling their reflected light. And this is a really physics-oriented game to model exoplanet atmospheres. It's really physics. It involves a lot of physics. And the basic way to model the spectrum of any exoplanet has it's like a machine. It needs some inputs and it gives out some output. And the inputs in the machine are, first, the thermal structure of the exoplanet atmosphere. By what do you mean by thermal structure? I basically mean that if you have an atmosphere, what is the temperature of the atmosphere with height? Okay, so Earth's temperature is hot. Then as we go up, the temperature cools down. Okay, and then after reaching a certain point, it again increases a bit due to the ozone layer, and then it again decreases. So that's the thermal structure of Earth's atmosphere. So if you want to model the reflected spectra or any exoplanet spectra, you know the thermal structure of that planet's atmosphere. So that's input number 1. The second input is the chemical structure of the atmosphere. How much water the atmosphere has, how much methane the atmosphere has, how much hydrogen, helium, nitrogen. You think of any molecule or atom, so that's all in the chemical structure of the atmosphere. The third part is the cloud structure of the atmosphere. Earth's atmosphere has water clouds. Okay, so if you wanted to model the Earth's spectra, then you would need that information, how those water clouds are, where those water clouds are, at what height those are. So that's this input. And the last one, oh, sorry about that. The last one is the bulk properties of the planet, like how massive the planet is, what is the radius, what is the surface gravity of the planet, and some star properties as well. What is the property of the host star, the temperature, mass, radius, and things like that. These are the inputs. But what is the machine? The machine is called radiative transfer. For those who are not familiar with radiative transfer basically tells you how light travels through a medium. Here the medium is the atmosphere and the light. So this machine basically calculates how light will travel to the atmosphere. And what radiative transfer gives you is, say, you have with this arrow, you have an incoming photon in the atmosphere from the star. This photon can either get absorbed by a molecule of water or oxygen, or it can get scattered. Then it can be a single scattering, or it can get multiply scattered like a random walk, and then come to you, the observer, like here. So this is what radiative transfer calculates. And the output is a reflection spectrum, like what I just showed you for Jupiter. So to model the reflected light, we need all those inputs and crunch the machine and get this output. So let me just walk you through each of these inputs quickly. So the first input I said you is the thermal structure of the atmosphere. As I said, that's temperature with height. And generally in exoplanets, we do not use height, but pressure, because with height, the pressure decreases in the atmosphere. The atmosphere becomes tenuous with height. So this is what we call the temperature pressure profile of the exoplanet atmosphere. And these are the temperature pressure profiles of the 3 exoplanets we have modeled. We have, of course, modeled these. These are not observed profiles. And you can see that the top is quite isothermal. The top atmosphere is isothermal in nature. The temperature remains constant with height. But the bottom has a function, and the very deep one is actually adiabatic with pressure. So this can be calculated with very detailed and robust modeling of planetary evolution, and that's where this comes from. Now, you might be wondering what these dashed lines in the backgrounds are, with chemical names written all over the place. So these are basically what we call condensation curves. If you have taken a thermodynamics course, you might be familiar with the Clausius-Clapeyron equation, which is an equation of phase change, how the phase change. So what this line shows you is a solution of that equation. Anything which is right, say, let's start with the water line. Okay, this is the condensation curve of water. Anything which lies here is water vapor. It cannot exist in water droplets. But the moment you go across this line, water will condense into droplets. Okay, and what water droplets in the atmosphere means is basically clouds. Clouds are nothing but droplets of water. So immediately by looking at this, you can tell that in each of the planets, what kind of clouds will form and where the clouds will form. For example, let's start with this orange one. This is the temperature pressure profile of that planet. And in this region, it is in the right of the water condensation curve. So here in the deep atmosphere, the deep atmosphere, water will exist as water vapor. But just when it crosses this line, the temperature is cool enough so that water will condense into tiny droplets. That means that in this exoplanet, at that height, we will start to have water clouds. But remember, Earth has a water cloud, but that does not mean that only water can form clouds. Clouds can be of many molecular species. For example, Venus has sulfuric acid clouds. You can imagine this is so bizarre, but Venus has clouds of sulfuric acid. Similarly, you can see that here, because for this blue planet, you see the condensation curve of ammonia. It cuts the condensation curve of ammonia. So that means that that planet will have clouds made up of ammonia as well as of water. So this is how, by modeling the thermal structure of the atmosphere, you can immediately tell that what will be the cloud structure of the atmosphere. So the cloud structure follows from the thermal structure. But that is not enough, because we do not know how the clouds will interact with photons. That's also important, because at the end of the day, we will be observing photons and not clouds themselves. So clouds mainly scatter photons. They can absorb photons as well, but they dominantly scatter photons. But what scattering means is the photon comes, it collides in some sense with the cloud particle and then goes off at a different direction. Now, scattering can happen in 2 ways, depending on the wavelength of the photon and the size of the scatterer. If you have the wavelength which is much, much larger than the size of the scatterer, then you get Rayleigh scattering. But if you have the photon wavelength comparable to the size of the scatterer, then you get Mie scattering, something called Mie scattering. And those can be very different, because in case of Rayleigh scattering, you get when a wavefront comes, it goes out as a something like a donut shape wavefront. But in case of a Mie scattering, you can get this very weird and beautiful shapes of wavefronts. What this means is, if light comes from this direction and the wavelength is comparable to the scatterer here, then this scatterer will scatter more light in the forward direction than in sideways or backwards. So this is a forward scattering scatterer. So cloud particles generally do Mie scattering in optical and infrared wavelengths. So we need to model that as well. So you can model that And what you need basically are three parameters: tau, g, and omega. Tau is the optical depth of the cloud, which basically tells you the number of scatterings a cloud particle will give you. Now the G is the asymmetry parameter, which tells you that if you have a symmetric wavefront falling on the scattering cloud particle, what will be the shape of the scattered wavefront? So here you can see that this is not at all a symmetric scattered wavefront. So this will have an asymmetric parameter, which is greater than 0. But in some cases, you can have isotropic scatterers as well. For example, in case of Rayleigh scattering, you get a dumbbell or a donut shaped wavefront, but to various approximations that can be treated as kind of isotropic as well. So that information is coded in this G parameter, which tells you the asymmetry of the wavefront. And then there's this parameter called single scattering albedo, which tells you how reflective the cloud particles are. Whether your cloud particle will reflect a lot of light or it will reflect a very small amount of light. So you do all these calculations and modeling. These have a lot of inner physics. And after all doing all of that, what you get is something like this, which tells you for each of the three planets, where and how much clouds will form. For example, you can see here that for the blue planet, the Epseri B planet, you have 3 decks of clouds in the atmosphere, 1, 2, 3. But for this green planet, which is the HD 62509b planet, you have only 1 deep deck of cloud. So depending on what exoplanet you are in, the cloud structure will be different. The optical properties of the clouds will be different. So this is the second input. And I'm not going into the chemical structure of the atmosphere, but yeah, there are ways to calculate that as well. Like given an atmosphere, what will be the chemicals or molecules in each height of the atmosphere? So we put all of these inputs into the radiative transfer machine and we get the modeled reflected spectrum of the 3 exoplanets. And this is how they look like. Of course, they're different because of different in their atmospheres. This one is very reflective because it has a lot of clouds, but you see a methane feature here. This one is a mixture of reflective and some molecular absorptions. And this one, as I said, that the green exoplanet had a very deep cloud deck. So it is not that reflective, but the cloud is too down deep in the atmosphere. So this is where our models take us, the predicted reflected light for each of these planets. So we are done with step 2. Now step 3 is to simulate observational data from this model spectrum. That is comparatively easy. You take the model spectrum, you decrease its resolution, because what you get from Raman Space Telescope is a spectral resolution of 40. Now, if you know the definition of spectral resolution, you would really think that this is a really, really low spectral resolution. 40, generally people working with galaxies and AGN do not use this kind of spectral resolution. That's not good enough for them. But this is what we get for exoplanets, especially for reflected light. So you degrade your spectrum to a lower spectral resolution first. Then also you add noise because telescopes will always add random noise to your data. Now the best signal to noise ratio we can expect from these missions is 20 and the worst is 5. So that's how you degrade the data and get your observational data out of this. So with this spectrum done, what you can do next is the next step, which is now I will blindfold myself and try to guess what is the amount of methane, water, clouds in each of these planets. And the way to do that, we basically use a Bayesian framework. Don't worry if you are not familiar with that, but that's not the most important part. What we want to do is to find the best possible way to interpret these observations. And how we do that is use 4 different models to interpret the observations, okay? These are not cloud models. These are ways to interpret. These are our, because I am blindfolded, I do not know what the actual cloud structure in that planet is. I can guess that it might be something out of 4 of these. The simplest one in the top is a single box-like cloud deck, as you can see. But of course, this is not real, right? This is just my best guess. That I can increase the complexity of my model a bit, I can have a profile, a triangular profile of the cloud deck. Then I can make it more complex. I can add 2 cloud decks. As we saw that some exoplanets have 2 or 3 cloud decks. So I can add that complexity. And the fourth one is even more complex due to some other properties I won't get into. But you can see that number of parameters for my models increases as I increase the complexity, of course. So with these 4 models, I will try to guess the best atmospheric properties using the Bayesian machinery. So let me walk you through those. So after we do that, what we have, I will show you the results for one planet because of time. But yeah, so what we have is, so these are the 4 models we are using. And the first thing I will show you is how we can best fit the data with these 4 models. So the top here one is the model spectra. This is not data, this is model spectra. Then if you can see these black diamonds here, this is the data from this spectra. And then I run this model on this data, and this is the red line here is the best fit spectra. Now you can of course immediately say that the model is fitting additional lines which is not present in the data. The model is not really fitting the data well. So this is an alarm for you, which tells you that the simplest model you used for your cloud is not good enough. It's not doing well. It's not fitting the spectrum well. The second most simplest one is also not doing well. It's also doing similar things. It's not fitting well, basically. It's not fitting your data well. But the other 2, they're doing a good job. At least they fit the spectrum, okay? But just fitting the spectrum is not good enough. I can just increase the number of parameters and still fit some amount of data, okay? So I need to see if they are guessing the right quantities as well. So let's start with the guess. So yeah, there you just say that, yeah, these are the additional absorption lines which they fit, which are not in the data. So let's start with guessing the molecules, right? Okay, so I will focus on 3 molecules: methane in this column, ammonia in this column, and water in this column. The red dotted line tells you the correct answer, the answer which was used to generate the data. And the blue shaded histogram basically tells you my guess, this model's guess. So you can immediately see that these 2 rows, they always overestimate. I always guess the water, ammonia, and water and methane to be more than what is right. And the reason behind that is because I was fitting all those additional absorption lines, and that's why I am overestimating these gases in these atmospheres. But so these are not working out. These are not at all working out. But in this complexity, when I use these kind of more complex models, I am kind of getting the right answer, except ammonia, which I'm not getting in any of the 4 models. And the reason behind that is ammonia doesn't have enough spectral signature, enough interaction with photons at these wavelengths. So I'm not getting it correct at this quality of data. So the bottom 2 models are working better than the top 2 models for this planet. Now let's see what they do about the clouds. So again, you have these 4 models, and the red line shows you the correct cloud profiles. Again, you can see that the first model puts, and the brown shades are my guess, okay? So you can see that the first model puts it really high. It's not working out. You are not good at all. The second model, it's working out. It's guessing the top cloud deck right. I have written it, this is not good enough because it doesn't guess the molecules right, like the abundances of methane and water. But yeah, it does okay with the clouds. It's not too bad, given that we don't know anything about the clouds. It's quite good. But see, the last 2 models, they are not getting the top deck right. Okay, their top deck is uncertain here and here, but they are getting the bottom deck very well. Okay, you can see that this is a cloud deck in the red, which was actually in the planet. And this is what my guess is. And that's really well, given that this is so deep in the atmosphere. This is about, say, 1 bar to 100 bars of pressure. Our Earth's ground pressure is 1 bar. And that means that with these models, in these kind of gas giant planets, you can see at pressures even below the typical Earth surface pressure levels. So that is great news. So these two models are really good in working out both the chemistry of these atmospheres and the cloud structures. So what this exercise basically told you that for a planet like 47 UMA B, you should not ever use the first two models to interpret the atmospheres. If you had done that, because they are simple, they're intuitive, what you would have done was to get wrong answers. So that's the goal of this work, to tell you what is the best possible model to interpret these observations. Now, I have done this for a case, the worst case scenario. The worst case scenario is where you have really noisy data. You can see that the error bars in this data is really high compared to the previous one. What happens then? The signal to noise of 5. Then, sadly, you cannot say anything about the atmosphere. You can see that all of these things we haven't got, irrespective of what model you are using. You are using two different models, but you cannot say much about the atmosphere. We have shown in our paper that we can say some things, very crude things, but that's the best we can do if we get this quality of data. But good news is the way the missions designs are working right now, we are hoping that if we will not get that bad data out of these observations. So we have completed all the steps. I will not show you more results from this work. There is a lot. You can go check the paper or talk to me if you're interested. But to just wrap up this part, so we construct and compare various models to interpret future observations of reflected spectrum. We identify the advantages and shortcomings of each of the models which are being used. And also what we find interestingly is not a model which is good for interpreting one planet is not always the best one for interpreting another planet. So with the 3 temperature planets I showed you, for this particular planet, the bottom 2 cases work well. But the other 2 planets, we find that both the middle and the third case, both of them work quite almost equally. Okay. So yeah, that was about the first part of the work. If you have any questions, I can just pause for a few seconds here.
Sagnick, I think you have to wrap up quickly, so okay, maybe we can. Sure.
Okay, sure. Yeah. So just moving on, this is the second part. This is still work in progress. And I will be talking about, this is a brief part, and I will be talking about probing polarized thermal light, probing atmospheres with another probe, not reflected light, but the planet's own light, but in polarized light, okay? Light which has some amount of polarization. So we are all familiar with this diagram where if a light is, unpolarized light is falling on a scatterer, depending on what angle you are looking at, the scattered light will be partially polarized or fully polarized, okay? So when photons are coming out from a planet, they will encounter cloud particles and gas particles, okay? And when a photon will scatter off a cloud particle, it will give you a me-scattering and some amount of polarization as well. So if you have clouds in exoplanets, you can get polarized light, thermal light from the exoplanet. Now, but that is not enough, because sadly, when you are looking at an exoplanet, it's just one point, a point source for you. You cannot resolve the surface of the planet. And sadly, if you have a completely spherical and uniformly clouded exoplanet, the net integrated polarization goes to 0. So to detect polarization from exoplanets, you need some kind of asymmetry in exoplanets. There are 2 ways to get that. One is if your planet is rotating really fast, then it's no more spherical, because due to centrifugal force, centrifugal acceleration, it becomes oblate like this. So fast rotation can break that symmetry and give you polarized signal from the planet's atmosphere, from the clouds. The second way is to break the asymmetry. Clouds never cover the entire of the planet in reality. Earth doesn't have clouds all over the place. So you can have something like this, patchy clouds on the exoplanets, and that also breaks the symmetry and gives you net polarized observable signal from exoplanets. Now, what we are trying to do is to see how that polarized thermal emission can tell us about clouds, the atmosphere itself, the planet's rotational velocity, and things like that. And the good news is both of these are very plausible because Jupiter is both oblate, it's not perfectly spherical, and also it has these cloud patterns. So you would get polarized light from Jupiter. So this is not uncommon to expect from exoplanets. So what I am here showing are 4 models with different cloud patterns. And of course, they show different amount of polarization. So by looking at the polarized signal of an exoplanet, which is a point source, you can actually tell the distribution of clouds on the surface, on the atmosphere of the the patterns of clouds on the exoplanets. And what we are right now doing is we have this recent study which shows that rotation and cloud patterns are not unrelated. Depending on how fast a planet is rotating, you get different cloud patterns. So we are using these model runs from this paper of cloud distributions to simulate the polarized signal from an exoplanet or a brown dwarf or an exoplanet due to these cloud patterns, and also the flux variability, because of course the pattern changes and the photons you get also will change due to that. So we are doing this modeling right now, and this is still a work in progress. And yeah, this will tell us a lot about planet rotations, clouds, and cloud patterns, interestingly, and weather, basically weather in exoplanets. And with that, I would like to thank all my collaborators. And yeah, so all of them have been involved with both the projects. One has been published, the other is still a work in progress. And also, I would just want to tell, since there are many undergraduates here, I would just want to point out about this resource called the NASA Exoplanet Archive. If you ever feel curious about exoplanets, just go to this website. This is a really interesting website. You can do whole lot of things just by browsing through this website. You can learn a lot and also do some hands-on work with exoplanets as well. So yeah, I would like to end with these 3 takeaway messages: that reflected spectroscopy is a window to cold giant atmospheres, and we have experimented with various model frameworks to interpret those observations. And we are now looking at another probe into exoplanet atmospheres, which is the thermal polarized light, to detect cloud patterns and weather in brown dwarf and exoplanets. And thank you with that.
Thank you very much, Sagnick, for this wonderful talk. So we can now move to questions. If you have any questions, please raise your hand or you can write in the chat box. Okay, we have a question from Asif Akram. Please unmute yourself, and the next is SSL.
Yeah, my question is regarding your third takeaway. So I probably didn't understand while you were talking. So how this thermal polarized light basically get detected, and what kind of characteristics of the planet, exoplanet? For example, how do you differentiate between exoplanet and a simple brown dwarf, or for example, simple dwarf stars kind of things? That if you can tell about that, yeah.
Okay, so you have asked 2 questions, which is first, how you detect thermal polarized light. So basically, thermal light is the planet's own light due to its own temperature. So light due to its own temperature, and those photons get scattered from the clouds. And in a scattering, you get partially polarized light. So that's how you get the thermal polarized light from exoplanets or brown dwarfs. And the second question is how you differentiate between brown dwarfs and dwarf stars and exoplanets. So the first order answer is brown dwarfs are bodies which have burned some amount of, which have undergone some amount of nuclear burning of deuterium, but very early while they were evolving. And planets are bodies which are not massive enough to do any nuclear burning. So that's the theoretical difference. But and there are, so the first way to differentiate between a brown dwarf and there is of course some overlap between these definitions, but basically if you look at the spectrum, you can tell whether that object, generally, whether that object is a brown dwarf or an exoplanet. But the theoretical difference is of nuclear fusion. And dwarf stars are basically stars. Anything which is a star means that has burned some amount of hydrogen. Otherwise, it's not a star. So that's the difference.
Well, I think we can move to the next question. SSR, sir, can you hear me?
SS, can you
Yeah.
Nice talk, Sagnick. I have a lot of questions, but I'll ask one only. So you are modeling the clouds with this scattering. What actually scattered? The molecule of water or the molecule of dust on which the water contains?
Yeah, that's a really interesting question. So it's not the molecule of water it's scattering, because then you have like a totally different way of scattering. So here it's basically cloud particles. And by particle, what we mean, the microphysics of those particles is what you said, that in the upper atmosphere, you have small dust particles, and water converts due to the due to the phase curve. So water converts from gaseous vapor to water droplets and accumulates on those small drops, and that's what you define to be a cloud particle. So the properties, the scattering properties of that cloud particle, even if that's water, will be very different from a water molecule, because it's no more, it's much more larger, a droplet of water, say. That's what it's scattering.
Okay, so no, the question I was asking because whether you are going to get the information about the water or the dust on which it condenses.
Okay, so right now you do not get info. So what information basically you will get is what is the refractive index of that droplet. That's all you get. It can be a bulk dust plus water or whatever, but what you basically get is the refractive index.
So not the amount of water
No,
you will be able to infer from that.
No. There are some models which go to the entire microphysics of these droplets and water accumulating on these droplets and producing those cloud particles, but that's generally used for solar system.
No, I
planets.
understand. That I understand. I'm just asking how much information you can extract from it.
Yeah, you can basically, the most you can tell is what is the refractive index of those part of that composite material. That's what I meant.
Thank you.
Yeah.
Orito Kundu is next.
Hi, Sagnick. It was a wonderful talk. So actually, I have three questions, but I will ask two, and if we have time, then we can ask another one. So can you go back to the slide where you showed the reflection spectra versus wavelength for Jupiter?
Okay. Let me see. Yeah.
That should be long back, yeah.
Yeah.
The Jupiter one.
Right. Let me just share that once more. Yeah, this one, right?
Yeah. So I can see that there is a distinct shape of the spectra that as we go towards higher wavelength, there is a decrease in the amount of spectrum. So why is that the case?
Oh, yeah, that's because of Rayleigh scattering. Because if you have no clouds, you only have gas molecules, and the wavelengths. So you are talking about 0.6 micron of wavelength, and gas molecules are much smaller than that. So what you basically get is mainly Rayleigh scattering, and that's like, you know, that with increasing wavelength, Rayleigh drops, right? It's omega to the 4, so it's inversely proportional to wavelength. So that's why you get that drop. But of course, just by Rayleigh scattering, you won't see that much of drop. So that's also because of those absorption bands. At those wavelengths, there are a lot of molecular absorptions of water, methane, ammonia, and those kind of molecules. So that's why the dip is even more like sharp. And interestingly, at shorter wavelengths, you see right around here, you see a positive slope, and that's because of Raman scattering in exoplanets. So yeah.
Okay. And another question was when you showed the um, temperature pressure profile for the three different exoplanets. Can you go back to this?
Yeah, sure. Yeah, this one.
Another one where you showed the probability density part.
Oh, okay. So there is no, there I do not have temperature pressure. There are molecules and stuff.
Okay.
Um, yeah, if you can like tell the question first, then I can
Okay,
probably
so
go to the.
I think it was in the third column for a particular molecule. So there is a shift in the red. Yeah, that one. Yeah. So I can see there is a shift in the red line for in the third column. Why is that the case?
Yeah, that's for water, and the reason because that shift is because water has formed clouds. So below this region, you have water in the gaseous state. This is only showing you gaseous water. As I said, once water from clouds, it loses its water identity. So below this, you had a gaseous water, but at this level, there has a cloud has formed in that planet. So it has consumed all the water in that. Up from that, it has consumed all the water to form water clouds. And that's the reason there is a dip.
Okay, I see. Thank you.
Okay, we have a question from Shomodi.
Hello, Sagnick. Can you go back to the methods where you see the exoplanets, transit method and etc. There you give a a graph of three colored lights. What does it mean? This one. Yes.
Right. So that's just looking at the star and planet at different wavelengths. By here, color basically means looking at 3 different wavelengths, and that's all that means. Yeah. There's nothing like the system is not like, yeah, by color, I just mean wavelength. That's it. Yeah.
And the picture in the right side also.
Oh, so okay. Oh, okay. So here in this picture, these are the data points, and then you have a best fit line. The blue is the best fit line. That's what the color means.
Okay, thank
you.
Yeah. Okay, we have a question from Moitre Kundu.
Yeah, so Sagnick, so I just have one question. Like in the exoplanet atmosphere, so there can also be some dynamics or turbulence. So how are these things theoretically modeled?
Oh, yeah, that's a great question. And that's what I showed towards the end. If you look at all those cloud patterns, so the way it's modeled, it's a very, very complex modeling. The way it's modeled is called general circulation models. It's basically fluid dynamics. And, like in Earth, we predict weather, right? And that's from some model. So yeah, that's basically atmospheric dynamics, which is modeled based on all the interesting fluid dynamics, which can go on in an exoplanet atmosphere, just like we model the fluid dynamics in Earth's atmosphere. Like we say that there will be a lot of winds, there will be rain and stuff like that. So it's basically fluid dynamics.
Okay, thanks.
Yeah.
Okay, I don't see any more raised hand.
But there's a question in the chat box from Shubhashis Dash.
Okay.
Could I read it? Yeah, I can read it.
Please.
So Sagnick, there is a question from Shubhashis Dash, who I think is our UG1 student. Why do we use IR rays? Why not other rays?
Right.
So
So that's a great question, and the reason is basically, if you remember Wien's law from black body emission, it says that the wavelength at which a black body peaks is inversely proportional to its temperature. Now, stars have temperature of something like 6,000 Kelvin, so you get a peak at optical wavelengths. But in case of planets are much colder, so the temperature is lower. That means the wavelength is higher. And if you put in, you can just do a small exercise and put in temperatures of some exoplanets or even solar system planets like Earth, Venus, Jupiter. And what you get as the peak is the infrared wavelengths. And that, since the planet is brightest in the infrared wavelengths, that's why we try to use the infrared wavelengths. If that answers your question. Yeah.
Okay, I think Sir has some more questions.
Yeah, since I don't see any more question, that's why I came to ask one more. So your albedo that you are calculating, is that depends on the surface of the planet, or it just depends on the atmosphere of the planet?
Right. For the planets I talked about, those are gas giants like Jupiter. They do not have well-defined surfaces. Those are mostly blobs of gas. So for these cool giants, they should not depend on the surface. But if you have something like Earth or terrestrial planets, of course, when you look at Earth from a space, you see some parts are blue. So if you have a surface, and if the atmosphere is not optically very thick above the surface, then the surface's own albedo will matter. That can cause the spectrum to look more greener just because you have greenery on Earth, or more bluer because you have oceans. So it depends on two things: if you have a surface, first of all, and secondly, if your atmosphere is not optically very thick, and then it will actually matter.
Thank you.
Yeah.
Okay, I don't see any more questions. So if there are no more questions, we can end this session and
Hi,
move to the
Navneet.
next
Can
session
I ask
maybe.
one more question?
Yeah, sure.
Uh,
Please go ahead.
So, Sagnick, you
Hmm.
mentioned three cases of your model, right? And
Yeah.
if I'm not wrong, the number of parameters were increasing with the models, right?
Right.
The different cases. So, I was wondering that you said the last two models were fitting the data more accurately,
Mhm.
and that also had more number of parameters.
Right.
So, isn't that bound to happen?
Yeah, that's a great question. That's a great observation. So yeah, of course, if you go on increasing the number of parameters, you will of course fit the data well. But yeah, there is a way to kind of check like if that is happening, called something called the evidence, which tells you that which basically balances these two things. Of course, like the kind of the reduced chi-squared kind of a statistic. The evidence is kind of that of a statistic that tells you that takes into account the increasing number of parameters and how well you are fitting. So even if you compare the evidences of those models, which takes into account that one model has a higher number of parameters than the other, you would see that those models are better, have a better evidence than the other two. Does that make it clear?
Yes, yes.
Okay.
Okay, so I think we're running a bit late for the next session, so maybe we can end this session now if nobody has any more questions.
That in the next session. So
Yeah.
we can end this session now.